three things that you need to know. We talk about a resistor or a resistance. We have a resistor, and then the second one we have a voltage, and then the last one we have a current. So everything that you are going to be asked, current, will be based on these things. Most of the things that they will ask, and then they also talk about cost and power over there. But the main thing that you need to know to at least get the marks, you must know what is a resistor, what is a voltage, what is a current, and how to calculate each of them. So in grade 11 or in grade 12, you also learned about the EMF, and then also the internal resistance. And unfortunately, all of those, they come from the basics: voltage, current, and resistance. If you don't know the basics, you can't talk about the EMF and the internal resistance over there. So, okay, say, where are you taking us to? In this case, the first thing that I want you to understand is that we have three types of circuits. The first one, we have a series circuit. Second one, we have a parallel. And then the last one, we have a combination circuit. But mostly circuit, whatever the spelling is, but mostly if you're in grade 12, you must be, whenever you study, you must make sure that you study the combination circuit, because it is the one that they mostly bring in the exams for your level. So I'm just going to quickly recap on what you see in a series circuit. In a series circuit, you will find that it is a circuit whereby the current remain the same throughout. Okay, just like that. And then let's say we have, can you come here, a battery over there. Let's say we have a battery over there, and then in that battery, we are going to be releasing the current. So your current will be moving in this way, for example. So what you will see, let's say your current is 1.5 ampere over there. That's the current that is moving out of the battery. So that current, it's going to move through your R1, your first resistance. Let's say, for example, your first resistance is 10 ohms. So your current is going to enter through that resistance. Okay, when that current enters, it's going to move out, and then the same current, which is still 0.5 amperes, is also going to enter through R2, for example, of which it might be 15 ohms, for example, and then it goes in like that and pass. So what I would just want to illustrate is that in a series circuit, you have current is the same. Then the second thing, what changes is your voltage. What is going to change is your voltage. Let's say, for example, you have V1 over here. I know my diagram is a bit messy, it's fine. You have V1, for example, it is, let me not put the readings. And then let's say you have V2 over here. So what is going to happen is that your voltages are going to be different due to the fact that the resistance are also different. Okay, what I'm saying is, for as long as you have different resistance, you will also have different voltage in a series circuit. Okay, so in series circuit, voltage is different. Okay, Because don't forget that when we talk about a resistance, we're talking about a device that opposes the motion of a current. It is actually something that is opposing the current, that is stopping the current from moving. Okay, so but when we come to a parallel circuit, our parallel circuit might be something like that over there, and then that is your diagram over there. So in this case, let's say your R1 is also 10 ohms, and then let's say your R2 is about 20 ohms over there. So now what's going to happen is, if you have a current, the same current of 1.5 ampere moving out of your battery, and then it comes out like that, that's your current moving. Actually, the electrons moving, because yes. So now, when that current arrives in that junction, this is actually where the current starts to split. Okay. So the first thing, in parallel, in parallel, current splits. Okay. So which means some of the current will have to move in this junction, and then some of the current, some of that current will come to that junction over there. So, but what determines the amount of current in each junction? What determines the amount of current in each junction? Okay, so when the current arrives here in this point, they're going to actually detect the amount of the resistance. Or okay, R1 is 10 ohms, R2 is 20 ohms. So when they detect the amount, when they detect that amount, they're going to decide, or okay, when we have a higher resistance, we can't move smoothly. It's going to be difficult for us to move because the resistance is very high. But when the resistance is very low, it will be simple for us to pass because there is less amount that is stopping us from moving. Okay, so what I'm actually saying with my English there is, the higher the higher the resistance, the higher the resistance, it means the lower the current. Okay, and then from there, the lower the current, the higher the resistance. Okay, the the lower the resistance, the higher the current. The lower the resistance, the higher the current. So these statements actually help you to see whether your answer is correct during the exam. Because let's say, for example, they ask you to calculate the current in that junction. They say calculate the value of the current and also the value of the current in that junction. So because this is 10 ohms, and then when your answer over here, it is your current over here, it is about 1 ampere. And then in this junction, you find that your answer is 0.5 ampere. You will ask yourself, because here I have a lower resistance compared to this resistor. Your R1 is 10 ohms and then your R2 is 20 ohms. It means that because R1 is less than R2, it means the current for R1 must be bigger than the current of R2. You see, so which means if you got the values like this, you can say your answer is correct, because the higher the resistor, the lower the current, and the lower the resistor, the higher the current over there. I hope it makes sense. I hope that makes sense. And the most important thing again to bear in mind is that for as far as you have you have the resistors in parallel, For as far as you have the resistors in parallel, the voltage is going to be the same. Voltage in parallel is the same. Voltage in parallel is the same. But in parallel, the current splits, which means here, current is different. Current different. So this is the most important basics that you must have. But what about a combination circuit? What about a combination? This is where it gets weird. So in a combination, let me say a combination circuit over there. Let's say we still have the same circuit, and then here we have that one, and then here we have this one, and then we also have this one over there. Right there, just like that. And then let's say we have a current value over there. This is our ammeter, which is measuring the current, over there. And then this is our R1. Let me say R1, R2, R3, R4. Okay, it's fine. So now what's going to happen? You're going to have your electrons moving out of the cell, or your charges, which contribute to your current. So, but I like to mostly refer it as the current. So you're going to have your current moving out of the battery over there. That's your current. And then let's say your current value, it is given as 2 amperes. You have your 2 amperes moving over there. So you will see that in R1 receives the total current, okay? So the statement that I want to write over here is R1 receives total current. And whatever that I'm saying here, it is very, very important when you answer the questions. You will see that it contributes to the logic that you need when you answer these questions for electric circuits. Okay, I said R1 receives total current. Then when that total current passes, that total current of 2 ohms is going to be splitted. It's going to split. Okay, so when that current splits, some of the current will move on the top branch, some of the current will move on the bottom branch. And the way they split is determined by the amount of resistance. The higher the resistance, the lower the current. But at the end of the day, you're going to have your current passing there. Your current passes, it moves, passes over there. And then again, your current meets again. It meets again. So this is actually what happens when you go through a breakup. You break up with your ex over here, or you break up with your boyfriend or girlfriend in that junction. The other one goes this way, the other one goes that way. That's why you separate. And then again, when you meet after a year and you see that your girlfriend is becoming the person that you ever wanted, so you're going to meet again and make the love. So when you meet again, you're going to be in the same relationship that you were once in. So which means that current becomes the same amount, which was 2 amperes again. Because when it was broken here, you might find that R2 was almost 0.5 and then R3 was about 1.5. So when they meet again, they contributed 1.5 plus 0.5 to make it 2 amperes over there. So that's what happens. And then again, R4 will receive total current. Total current is received over there. So what you will see is that in a combination circuit, other resistance receive total current, other resistance, they have to split the current over there, and in order to share it. As simple as that. But okay, there is a case whereby they require you to explain. They will ask you to tell them what happens if we have removed a resistor, or what happens when we have added a wire, something like that. Let's talk about that case. Let's talk about that case. Let's say effect when the effect when a resistor, or let me say effect when resistors are added. I'm not yet talking about the internal resistance over here. I'm still talking about the basics, because I know with internal resistance, it becomes very easy if you understand the basics first. So you have a simple circuit over here. Let's say we're adding resistors in parallel. Effect of adding resistors in parallel. Okay. We have a simple circuit. Let me just draw the resistors over there. And then the statement says we have added another resistor. We have added another resistor. So this one, the red one, it is added. So what actually happens when we add resistors in parallel? It decreases the total resistor value. That's the first thing that you need to know. Okay, so let's assume that our R1 was 5, and then our R2 was also 5, for example. And then let's say R3 is actually 3. We have added 3 over there. So the first thing that you are going to do to verify that what I'm saying is actually correct, we're going to find the total resistance for R1 and R2. That is before R3 was added. Okay, so before adding R3, adding R3, I'm going to calculate the total resistance, of which RT is made up of R1 multiplied by R2 divided by R1 plus R2. This is the formula that you do, that you use when you have two resistors that are connected in parallel. Okay, so then your R1 is 5, and then your R2 is also 5, and then that is 5 plus 5. What is the answer that you get from your calculator? What is the answer from the calculator there? Can I please get the answer? Is it 2?
5 over 2. 2,5.
5 or 2.5? Okay, thank you. That is 2.5 ohms over there. So you see, that is before adding R3. But let's calculate when we have R3 now. Let's calculate the total resistance now and see what happens. Okay, I'm going to say RT now. Unfortunately, because now I have 3 resistors in parallel, what happens is I can no longer use that formula. I'm going to use the formula that says R parallel is equal to 1 over R1 plus 1 over R2 plus 1 over R3 over there. And then 1 over 5, that is plus 1 over 5, and then that is plus 1 over 3 over there. Can you guys please do the maths for me and tell me the value that you get over there?
0.73.
Is it the final answer, or is it before turning it upside down? And
Before.
okay, before. It is what? 0.
73.
0. Is it not 1 over something?
11 over 15.
Oh, okay. That's 11 over 15 over there. But what you will see is that that value, it is 1 over r. It is not your r parallel. It is 1 over r parallel. So you are going to turn this upside down because you know, according to mathematics, if I say 1, if I turn this upside down, I'm going to have 1 rp divided by 1, of which it gives me simply rp. That's mathematics. Anything divided by 1, we can just leave it as that thing over there. Just unfortunate, I was not that good in mathematics, so I'm just going to be straight to what I'm good at. And then you are going to turn this upside down. You will say 15 over 11. And then what answer do you get?
1,36.
1.36 over there. So now look at the values that we got. Before we added R3, the value was 2.5. But after adding R3, it is 1.36 over there. So someone maybe was thinking in a different way that when we add resistors, the total resistance will increase. No, in parallel, it decreases. Okay. So the first thing that you have in this case, effect when resistors are added in parallel, the first thing that happens, RT, or the total resistance, decreases over there. Then the second thing, don't forget that in this topic, we have only one law, of which it is Ohm's law. Ohm's law. Even though you don't know what Ohm's law says, at least please know what Ohm's law is in terms of the formula. You must know the formula of Ohm's law, which says R is equal to V over I. You must know this formula by heart. This is Ohm's law. It says that resistance is inversely proportional to the current, given that temperature is kept constant. That's what I know. Resistance is inversely proportional to the current at a constant temperature, which means that when the resistance increases, the current decreases. That's what happens. So if your resistor or your total resistance has decreased, it means that your total current, your IT, is going to increases. Your IT increases. But what about the voltage? What about the potential difference? What about it? The way I do it, I know this formula says V over I. I know this formula. But what I do, I'm going to divide that side by 1 because I know any number has a denominator of 1 according to mathematics. So I'm going to use this theory. I have R on top. I also have V on top. So those two that are on top of the fraction, I mean the numerators. Numerator is the number that is on top on a fraction. They are directly proportional to each other. Whatever that the resistance does, the voltage also does. Okay, that's true love. Whatever that your partner does, you also do that. So which means voltage, or the total voltage VT, decreases. It has to decrease because the resistance is decreases over there. So whatever that the resistance does, the voltage also does that thing, because both of them, they are on top of the fraction. That's how you cook. And when we talk about the internal resistance, we're still going to talk about the very same thing, just that there will be only one few thing that we add. And that few thing is simple and straightforward over there. So That's how you answer them when they say, maybe for example, if they have changed the equation and say effect when resistors are removed in parallel. When we remove resistance in parallel, what's going to happen? The total resistance is going to increase. Okay, when we remove resistance in parallel, that total resistance will increase. Okay, let's assume that we were having R1, R2, R3, and the total resistance that we got was 1.36 over there. But now we are removing R3. When we remove R3, our total resistance is going to be 2.5, which means the total resistance has increased. And when total resistance increases, let me also add it over here. You will do your summary. RT increases. When RT increases, what about my guy? Oh, current. Current, which is IT, is going to do what? Decreases over there. What about voltage, who is in a relationship with the resistance? The voltage will say, nah, my love is increasing. I also have to increase. So VT is going to also do what? Increases over there. So this is what happens when you remove R in parallel. So that's how you work it out. As simple as that. Simple as that. But let's talk about a series, because I only talked about a parallel over there. Let's talk about a series circuit. Just in case, I'm sure we still have a lot of time over here. So that is R1, R2. I'm not writing any value over there. So what happens now? We're going to adding R in series. So the added resistance, I will indicate it using a red line. This one is added. Now, what's going to happen? This is the question. What's going to happen? Don't forget that in a series, in a series circuit, the total resistance is just the summation of the resistance in that circuit. Wow, what do you mean say? I mean that RT is actually the summation of, let me say this R3, is summation of R1 plus R2 plus R3. That's the total resistance in a series circuit. So it means that if my resistor over here was 5 and my resistor here was also 5, and then this one is 3, I'm using the same values. Before adding, before I add, let me say before adding, I'm going to calculate my total resistance. No, my total resistance, it was 5 plus 5 over there, which gives me 10 ohms. This is my total resistance before any addition. But okay, so now I'm adding a resistor, which is R3 in that circuit. After adding, my total is going to be RT is going to be 5 plus 5 plus 3 over there, of which it is the one that I added. This gives me 13 ohms, which means when I add in a series, RT increases.
Sir, you are muted.
Yes, I see a hand, by the way. You can ask over there if you have a question.
Hi, sir. I wanted to ask if when we are writing like the total resistance increases, aren't we supposed to include the internal resistance, the effect on that?
Oh, that is when we have the EMF over there. Just that now I'm still talking about the basics. But with that one, when you talk about the EMF and the internal voltage, it's not that much of a problem. I can also summarize it for you right now. But for now, I wanted to remain on the basics, like the basics themselves. But okay, it's fine. I'll also show you what happens. I'll tell you what happens with the internal. Let me also mix it up now. And please, the person who is muting me, can you please behave at least for today? At least for today, allow me to teach. If maybe you want something like money, come to my inbox and say, I want money instead of muting me here. You can see that I'm not looking for any money right now. But if you want money, come to my inbox with your bank details. I will assist you instead of muting me. I don't understand why you're doing this, but it's fine. I know this kind of people. So what I was still saying is the voltage is going, OVT is going to do whatever that the resistance is doing. Okay, so which means also our voltage is going to increase over there. But now, though, just to mix it with the EMF over there, you know that EMF, it is actually the maximum energy provided by the battery per unit charge. Okay, the EMF is equal to I, or let me start over here. EMF is equal to V internal plus V external over there. This is what the EMF is the maximum energy provided by the battery per unit charge. That is what you have when you buy a battery. That's the EMF. What I'm saying is, you are going into a shop, you buy a battery, it has a certain amount of energy that it can provide. But in that instance, it does not actually provide the total energy that is written there. Let me give you an example. You go into a shop, you buy a battery rated 13 volts. Your battery can only provide something like 12.8 volts, and then it dies out. Then the question is, what about that extra 0.2? Okay, where is 0.2 V? This is the biggest question in this topic. That 0.2 V is taken by the internal resistance, of which it is the resistance of the battery itself. A battery has a resistor over there. So now what happens is, when we calculate these things, when you do the calculations over here, you are going to further break this formula down into, you know that this is the external, and then this is the internal. So for internal, V int is equal to IR, and then for V external is equal to IR. Okay, so I see something similar in both of them. What do I see? The total current, the big capital letter, which is the total current over there, which means this is what happens. Very, very important. Very important. Let me add it over here. You have your internal resistance over there inside your battery, something like that. What you need to see, or what you need to identify, is that you're going to have your current moving throughout your circuit moves like that. But what I want you to know is that the internal resistance, this thing, your internal resistance will always receive the total current, always receive all total current. This is very, very important. It's more important than the person you are currently in a relationship with, because that person might leave you, but this statement might give you marks of which you might need them next year when you apply for university in order to come and find your soulmates over here. Okay, I'm joking. So now, what I'm actually showing there is that there is a relationship between the total current and the internal resistance. Internal resistance receive the total current in a circuit, okay? But another important thing, every battery that you buy, it has a certain amount of the internal resistance, which means internal resistance is a constant value. This number, this one is constant. It remains constant throughout your question. You can never find an examiner saying we have changed an internal resistance. Highly impossible, very impossible. So which means if I have a formula which says V internal, V int is equal to IR, what's going to happen here? The thing that is going to happen, I can only manipulate the internal voltage and the total current, but this value remains constant. I want you to understand the maths now. Now we're talking about mathematics. I can only manipulate the internal resistance. I can only manipulate the internal voltage and the current, the total current. So what do you mean? I mean that if my internal voltage changes, maybe let's say I started with 2 that side. I started with 2 volts that side. And then my current over here, my total current was actually, let's say my total current is 2 to make the math simple. But my internal resistance was 1 over, in this case, my internal resistance was 1. What you will see is that my equation is balanced. I have 2 this side. I also have 2 times 1, which gives me a 2 over there. All right, we are fine. But now let's say this internal voltage increases. Now the internal voltage is increasing. So what you will see is that when the internal voltage increases, let's say now it increases to 4. But this side, what is it that can change? It's only the total current, because the internal resistance remains constant throughout. Internal resistance remains constant, as I've stated over there. So which means I can only change this total current to balance the equation. I have 2 this side. I have 2. I want to make it 4 so that it balances. What's going to happen? I'm going to increase the total current. Total current increases to 4 because my internal resistance remains constant throughout the equation. So which means I still have 4 is equal to 4 multiplied by 1, which is simply a 4. My equation is balanced. So what you will see throughout your whole life is that whatever that the current does, the internal voltage also does that thing. That's me talking English over there. Whatever in your equations that the total current does, your internal voltage does that thing. Okay, so let's come back here. In this case, okay, let me get back a bit. Okay, we said effect when resistors are removed in a parallel. And then I said, when we remove resistors in parallel, is there something? Anyone want to say something? Okay.
So
Okay.
does it mean that current is directly proportional to internal resistance?
Exactly. Very much accurate and very much perfect. Right there, you are a true scientist. You have just identified my famous and most beloved statement. I love that statement. Total current is directly proportional to the internal voltage. Yes, that's the statement of the year. So whatever in the notes that you were writing, I want to make it quick. Whatever in the notes that you wrote, whatever that the current did, the internal voltage also did that thing. Just that English. So which means here, because our total current decreased, it means that V internal is going to also do what? Decreases. So if you ever go in exam or in a test or when you're practicing something and you find that current and internal voltage are inversely proportional to each other, come to talk to me. I'll give you a very good award for sure, because that's what I know and what I've ever seen across my whole life in matric and even this year. So which means here V int was going to do what? Increases. Here, what about it? V int was going to do what? Decreases over there. And what you will see is that this is almost a 4 marks in the exam, almost 4 or 3 marks. Because if they want you to choose from decrease, increase for resistance, you are going to get 1 mark. And then they say explain. You have 3 explanation, you get almost 3 marks. So there, your life is simple over there. So, okay. Before we go any further, let me now talk about this formula in details. EMF is equal to I into R plus small letter r over there. And then this formula actually comes from, some of you knows this formula, EMF is equal to V int or Vx, whatever, plus V int. And then when you break this one down further, it's going to be EMF is equal to IR plus IR, of which it will come back here because you just take a common factor of I over there. But what does this mean? It actually means, okay. This is actually some sort of mathematics involved in this case. There is a bit of maths involved over here, of which I will make it a bit simple for you guys. Let's say we have a graph. Graph of V, or the voltage, Vs, the current over there. So let's say, yeah, the voltage. Okay, it's fine, even in this case. So I'm going to do it very simpler. As long as you do follow what we'll be doing, I'll be pleased. So let's say, because it is a graph of voltage versus the current over there, let's say here we have the V external, which is measured in volts. And then here we have the current, IT, which is measured in ampere over there. So what I want you to know is that this graph is going to be a straight line. So for those who are doing statistics in grade 12, sometimes it obeys that thing, scattered plot. It's not scattered plot. That one for statistics. I forgot that graph, but it's fine. Doesn't matter, even though you don't know. But what you need to know is that it is some sort of a straight line graph. It's going to be a straight line graph over there. So let's say now we have the values over here. We have at least 0, 1, 2, 3, 4, 5, and then 6. And then here we have about let's go. Let me make it 1.2, 1.4, 1.6, 1.8, and then 2.0, and then 2.2. It is in 222 over there. I want us to work some maths over here. But first of all, let's say I've drawn my graph as something like this. There are points over there, and then points over there, points over there. Now, whatever calculation that you're going to do over here in this case, in when you are doing the graphs, you have to know that the graph is a straight line, okay? And you know that according to mathematics, a straight line graph has the equation what? Y is equal to mx plus c. This is a straight line graph, okay? According to mathematics, a straight line graph has an equation y is equal to mx plus c. But what is c? This is the y-intercept. What is m? This is the gradient. And then that is just your, is it y-axis, x-axis, whatever. I don't know. I forgot. It's fine. And then now, don't forget that a gradient is constant in a straight line. This one is constant. So which means now, someone already know that my gradient is going to be the internal resistance at some point, or someone might say it's going to be an EMF, because EMF is also a constant value. And it is the maximum energy provided by the battery. So if the battery can provide 12 volts written, I can never change that. That is the maximum energy it can ever provide. So which means an EMF is also a constant value, okay? EMF remains constant. So which means now you are going to identify which one is your gradient. Your gradient is the internal resistance. Okay, well, let me do this. I'm using the same straight line equation. Y is equal to mx plus c over there. And then this is going to be my EMF is equal to V external plus V internal. Okay, so what are you saying? I'm saying that an EMF is the maximum energy provided by the battery, which means it is also a voltage when there is no current in the circuit, okay? Because you know that if I have a circuit and the switch is open, the voltage that is measured is the EMF. I hope you know that, okay? Okay. When a circuit has a switch open, the voltage that we read is the EMF. Okay, say I don't understand why are you bringing this statement in this case? Okay, the reason why I'm saying this is because look at my graph. My graph starts at V being equal to 1.8 volts. Okay. But what is the X value? What is the value of the current? It was 0. The value of the current was initially 0, which means it is some sort of the switch was open, because when a switch is open, current cannot flow, which means there is no flow of current when a switch is open, which means we are measuring the EMF in that case. Say you are a genius. Thank you. Okay. And I know. So what I'm actually saying is that when I am on the okay, so what I'm saying is that when I am on the y-intercept of my graph, I'm going to be measuring the EMF, which means I measure the EMF on the y-intercept. What did you say? I said on the y-intercept we measure the EMF. Okay, over there we have our C, which is our y-intercept. Okay, say, which means this C over here, it corresponds with the EMF over there. Say you're a genius. Okay, thank you. Again, which means I'm going to transpose. I want to rearrange this equation. I want to rearrange this equation in a good way. I'm going to write my EMF over here. EMF. It is my C in this case. So let me write it here. EMF plus. But say, because now we have the constant value, Angiti, I said we have a resistance, which is internal resistance, which is constant. We also have the EMF, which is constant. But this constant value, we have found that it is our y-intercept. Okay, that's fine. Which means the other constant value will be our gradient. Okay. Which means the other constant value, which is the internal resistance, is going to be our gradient. How is it a gradient? Because if I have V int, this is equal to IR over there. IR, something like that. So which means over here, in this case, I'm going to have what? I'm going to, in fact, I didn't rearrange it correctly. When I transpose it to that side, it was supposed to be negative, which means this is wrong. My EMF over here, when I take it to that other side, it's going to be negative EMF over there, or negative EMF. It's fine, like that. Yeah, all right. Then now, because I have transposed EMF to the other side, now I'm going to take this V external to one other side. I don't know if, okay, I will explain again what I'm doing over here. I'll explain again in a simple way that all of you will understand. Let me explain it over here without any complication. The first thing that you need to identify, what is my Y value? My Y-axis is made up of the external voltage. That's the first thing. First thing, my y-intercept is made up, my y-axis is made up of V external, which means according to y is equal to mx plus c. This one is made up of V external. So that one is V external over there. And we have already discussed that according to the formula, EMF is equal to IR plus I capital letter R. This one, it is my C value. It is my y-intercept. That one is my y-intercept. So which means I'm simply, in order to rearrange this equation in a good way, I'm simply going to take that one to the other side. I'm going to transpose I and small letter r to the other side. And you will see that mathematically, I'm going to have the equation. So which means I'm going to do what? I'm going to simply take this to the other side and it becomes negative, which means now I have I, R, and then mathematically it must be negative when I take it to the other side, because here it's positive. When I transpose it, it becomes negative plus, and then the EMF over there. Okay, yeah. Now here's my equation. Look at the equation now. What I simply did in this case, I only took IR to the other side, and then I'm left with V external on one side, Vx on one side only. So which means your equation is going to be something like this. Your equation is like this, because this one is your y-axis, V external is your y-axis over there. And then what about your x-axis? Your x-axis over here, it is your current IT, of which it is this one. And then your R is the gradient. Your R is the gradient over there. The M is the small letter r over there. And then C is actually your EMF. C is your EMF over there. So that's your equation. If you want, you can write it like this. Vx is equal to negative R I plus the EMF. you are still very much correct, because you will be obeying the straight line equation formula, which says gradient first and then x after over there. So whatever calculation that you're going to do with the graphs, you're going to work using that formula over there. Very important. Now let's talk about the cost of electricity, or let's first talk about the power. Okay, we have the term power. What is power? Power is actually the rate at which work is done. Rate at which work is done. So which means the first formula that you're going to work with in this topic, it says P is equal to W over delta T. And did you know that when we say rate of something, it means that we're dividing by time, and then work is shown by W. So it is the rate we're doing work per unit time. That is power. Work done per unit time is the power over there. So this is where now we're going to talk about the cost. The power brings us to the cost in some ways over there. But let's first talk about it. What do we actually do in this case? Or what do we actually have? You have a lot of formulas that some of them, I am not even going to talk about them. You will find them in the exam. Let me give you the unit for power. Power, we measure it using watts, W. It's power measurement. And please note it very well, NB. When we calculate power, we use watts. But when we calculate the cost, we're going to use what? The kilowatts. So it's very important to differentiate the two things. We use power, when we calculate power, we use watts. For cost, we use kilowatts over there. So now, what is this other thing that I can give you? Okay, you know that W is equal to V I delta T. This is one of the formulas for W, or for work. So if I want to rearrange this equation over here, I can come and say power is equal to, in the place of W, I place V I delta T divided by delta T. Delta T cancel over there, and then I'm left with power is equal to V I over there. This is what I'm left with in my equation. Okay, just a bit. Just a moment as I connect my charger off. Sorry about that. So now, not even laptop battery formed against us shall prosper, according to the Bible. Not even the battery power can make the lesson end. Okay, so now you know this formula, it is very much famous. P is equal to VI. And then that's where you start to rearrange the equations, and then where you can put V is equal to IR. In the place of V, you come and put P is equal to IR multiplied by I. And then this I and that I, they're going to make I squared R over there. So you can just play around with the formulas. You manipulate the formulas and then you get what you want. So that's as simple as that, how you can make it. But okay, let's say, let me just quickly add the cost over here. I want us to do the equations. I want us to see how, or what I'm saying, is it on the equations. I want us to go there. So now, let's say you also need to talk about, we also need to talk about the cost of electricity. So for cost of electricity, what you need to know, or what you need to just have in mind always, is that cost is equal to PTR. Okay. Yes, PTR. As simple as that. So now, here, P, it is the same power, that we discussed above. That is still the same power. And then here, it is power in kilowatts. And then this one, this is our time now. It is measured in hours. So in this case, for power, time is measured in seconds. But for the cost of electricity, time is measured in hours. And then this is the cost, this is the amount in rands. So sometimes you're going to be given in cents, in maybe 100 cents, 90 cents, whatever. So you just have to play around with the maths over the conversion, as simple as that. So now let's say you are asked to find the cost and you can find the power. It means that the first thing that you're going to do, you're going to find the power. The second thing that you do, you find what? You find the time. Mostly your time might be given in minutes. If you are given the time in minutes, you have to convert it into hours. And you know how to convert it into hours, I guess. So your cost is also going to be in rands over there. And then that is all that I can give you, other than without questions. We'll find examples in the question for sure. And then we see what we have from there. I don't want us to get tired before doing a lot of questions. So far, is there anyone with a question? Is there any question so far? Yes. I see a head. And I don't hear anything.
When you say that we should convert to rands, do you mean it should always be like the whole number? It shouldn't be like 50 cents. It should always be like in the whole number form.
What I actually mean is, okay, yeah, something like that. But at some point, let's say they gave you 90 cents. You have to convert 90 cents into rands. What I'm saying is we use the rands only. We don't use cents. So because if you convert 90 cents into rands, you're going to have a number that is in decimal forms. Because to convert from cent to rands, I think you divide by 100. And then I think here you're going to get what? 0. Is it 0.9? I think you get 0.9. So it must always be in rands. That's the unit over there. So it does not necessarily have to be a whole number. It can be in something with decimals as long as it is in rands. I find.
Yes, thank you, sir.
All right. Then if there is no other question, let me quickly come over here. Oh, and by the way, it's fine. I will try to show it on the calculations, because I did it during one of the lessons, and then one of my learners said teachers does not allow the way I was calculating the current. You know that there is something like, is it a law or a principle? Current divider rule. So one of the learners said it is banned. I don't know whether it's this year, because last year it was allowed, whereby maybe if you are looking for a current that is passing through, let's say this resistor, for example, we are going to say current passing through that resistor is going to be equal to current passing to the opposite resistor, of which, let's say, I'm going to just take 20. You take 20 and then you add the summation. You simply add or take the sum of those resistors, of which it might be 20 plus R, then you multiply by IT over there. But I will show you in calculation that you're going to get the same answer. But if you are advised not to use it, then don't use it. So I'm going to read the questions for you, whereby you find that my English is bad. Just accept the situation and move on. Just like when you went, okay. A battery with an internal resistance of 1 ohms and unknown EMF. Okay, we have an internal resistance of 1 ohms. Internal resistance constant. What is the EMF? Unknown. We don't know it. Then is connected in a circuit. An unknown EMF is connected in a circuit as shown below. Okay, a high resistance voltage. A high resistance voltage is connected across the battery. Okay, which is this one. They simply mean that resistance over there. Okay, and then now A1 and A2 represents ammeter with negligible, yes, resistance over there. That statement, does it actually play a role? Doesn't actually matter, but it's fine. Now, the first question says, or the another statement says, with the switch S closed, the current passing through 8 ohm resistor is 0.5 ampere. Okay, they said as soon as this switch is closed, the current that is passing through the 8 ohm resistor, it is 0.5 ampere, ampere, yes, ampere over there. And then 4.1 said state Ohm's law in words. State Ohm's law in words. What does Ohm's law says? Ohm's law says current passing through a conductor is directly proportional to the potential difference at a constant temperature, whatever, just go and use your exam guideline over there. You will get the correct definition. It's 2 marks. It's 2 marks. Okay, so then the second question said calculate the reading on ammeter A1. Okay. They want us to calculate the reading on A1, but what is it that we have we can use to calculate the reading of that ammeter? For my case, I think we need a resistance, we need current, we can find the voltage in this case. Because, okay, well, what I'm saying is, if I can get the voltage for this, if I can get the voltage value over here, I can simply find the current, but I don't have the voltage on that one. It means I have failed. But in this case, in this other branch or in this other section, if I can find the voltage, okay, well, if I can find the voltage, provided that I have resistor which is 8 ohm and current which is 0.5. If I find the voltage on that section, that voltage is going to be the same as the voltage over here. Say, what do you mean? I said that in a parallel circuit, voltage is the same. So the voltage that we will get here will be the same voltage that we will get in that section. Voltage is the same in that parallel branch, which means if I have the voltage, if I get voltage for that section, I can find the current. And that current, I simply add it to that current of 0.5, and then I get the correct answer of my current over there. Say, I think you have just spoke a lot of things. Okay, it's fine. Let's work it out. What am I going to do? I'm going to find the voltage here. I need the voltage of the 8 ohms according to what we did when we're still talking about, if you remember, I showed you the difference between series, parallel, and combination circuit. And then I said in a parallel, voltage is the same, remains the same. So which means to find the voltage, I'm going to say V is equal to I, R, and then what is my current? In this case, I have 0.5. And then what is my resistance? It's 8. And then what is my answer? What is my answer? What answer do I get from the calculator?
12.
It's going to be 12 volts. So now, if I have 12 volts, the 12 volts that I got here, 12 volts, is the same
Sir, it's
as,
actually 4. It's actually 4, sir.
4.
okay, it's fine. Thank you. 4. All right. So that's going to be 4 V over there. And it means that my voltage over here is also going to be 4 volts, because in a parallel circuit, the voltage is the same. So now I can simply find the current in that is passing through this branch over there, because what actually happens is there's going to be a current that moves out of my battery over there, and then that current arrives to this branch. The other current goes that way, the other current goes this way, and then again I still have another branch. Some of the current will move this way, and then some of the current going to move through the 16 ohms, and then they meet again. When they meet, they contribute to A1. So which means A1 is actually the sum of the current passing through 8 ohm and 16 ohm. I hope that makes sense. A1 is the sum, is the addition of the current that passes through 16 ohms and 8 ohms over there. That is why I said we're going to calculate the current passing through 16 ohms using the same formula. V is equal to I R over there. What is my voltage? That's 4. What is my current? I don't know. What is my resistance? That's going to be 16. And then I simply divide both sides by 16 over there. 16. And then cancel, cancel. I have I this side. And then what is 4 divided by 16?
1/4.
1/4. And then in decimal,
0.25.
0.25. I'm ampere over there. So now in this section, I have 0.25. And then in that section, I was having 0.5. They have given me. So I need to combine in order to find the total current. It's actually IT. I mean total current for this branch. Or let me simply say current passing through A1. Let me say A1 so that I don't confuse you guys. I'm talking about the current passing through A1 is going to be the current in 8 ohms plus the current in 16 ohms over there. So I hope I didn't confuse you guys over here. So which means I'm going to simply add 0.25 plus 0.25 over there. Oh, 0 and 0.5, not 0.5 over there. What answer am I getting?
0/4.
0.75.
0.75. A. So, which means that is going to be your current that is passing through A1, which is 0.75 A in that case. Okay.
You are muted again, sir.
All right. All right. So if device R delivers power of 12 watts, calculate the reading on A2. Now we're looking for the reading on A2. So in this case, what you can simply do, I think there is a lot of ways that you can work out this equation, but one of the simple ways that I see is if I have the power, and then in that power, it is 12 watts. And then what about the resistor? I don't know the amount of the resistor, but I have the information of the branch above, of the top branch. I have every information, but also one of the simple way that we can do, or that we can work with in this case, I suggest that in a case like this, we can find the parallel resistance or the effective resistance by using this formula, by using this formula. Rp is equal to R8 ohms multiplied by R16 ohms divided by R8 ohms plus R16 ohms. So we can find the resistor of this branch. It's even messed up. Let me clean a bit. Yes, we can find the resistance over there. So after finding that resistance, we can add it into that with that resistance, because from there it will be now in series with each other. Okay, let me just write what I'm saying. I'm saying that if I make the calculations here, I say 8 multiplied by 16 divided by 8 plus 16. What answer do I get from the calculator? I'm
5 point
simply, okay,
3,
5.33.
3.
All right, thank you. That's 5.33. And from there, it means that now this is going to be a simply one whole resistor. I simplify into one whole resistor, which is 5.33. 5.33, which means I simply remove the parallel and make it a series, make it one resistance. You simplify a circuit over there, 5.33 now. So what you will see now is that your circuit does something like this. That's going to be 5.33, and then here you have a 20, and then it continues whatever. But what you will identify is that now the these two resistance, they are in series with each other. They receive the same current. They're going to now receive the same current, which means in a case like that, if you are looking for the total resistance of that branch, you are going to simply say RT is equal to 5.33. I mean total current for this branch, not for the whole circuit, plus 20. This will give you 25.33 as your resistance over there. That's fine. So now, if we are still on the same page, you will realize that A1, the current over there was 0.75. That was the current of A1 over there. And then what is the resistance of this branch? It is 25.33. Okay, say, which means in a case like this, I can simply find the voltage. Yes, I can simply find the voltage. Okay, so if I am looking for the voltage, I'm going to say V is equal to IR. Why am I looking for the voltage? Because this whole branch over here, or let me use blue, this whole branch over here, I simplified it into 25.33 as my resistor. Now, that 25.33, it is in parallel with this resistor, which is R2. So resistors in parallel, they have the same voltage. That is why I'm looking for the voltage over there. So this is the logic that you need when you're working with electric circuits based equations. Okay. So which means, what is my voltage? I don't know. But what about my current? My current is, where is my current? 0.75. 0.75 multiplied by, what about my resistance? That 25.33 over there. And then what value of V do you get from your calculator?
$18.99.
That's 18.99 V over there. So now, in that case, we have the voltage value of the top branch. It's going to be the
Afternoon,
same.
sir.
Yes.
May I please, I hope you're well. May I please ask a question?
Yes, you're free to ask.
If my decimals are not like continuous, like they have a short span, do I need to round off?
No, according to your question paper, the instruction on the question paper, they say round the final answer into 2 decimal places. So you're actually not allowed to round off in the middle of your question. But somehow you can round, but as long as the values on your calculator, you don't round them. So what I'm saying is, if let's say, for example, I got 0. I have 225.33333. I'm going to
Yes.
write 25.33. I write 25.33, but on my calculator, I don't use 25.33. I use that value of 25.33333 to make the calculation, because maybe whatever that I wrote might be different from the answer, because on my calculator I was not rounding, but on the question or on my answer sheet I was rounding, of which it can also be dangerous, because what if the person who's marking the question paper takes the calculator and prove, or your calculations are valid, or your calculations are the same? I don't know if I make sense, but don't round in the middle of the question, please. Just write the entire number that you have.
Okay, sir. Thank you.
Yes, because I don't want to mislead you. The instruction says round off the final answer into 2 decimal places, so you don't round in the middle of the question over there. So yeah, that's also a good question. But in this case, because we're just practicing here, let's round off. Let's not use long numbers. So we had the voltage value over there. But let's come back to our question. Our question said, if device R delivers power of 12 watts, okay, calculate the reading of ammeter. So now, because for that device R, we have the voltage V, which is 18.99 volts. It means that, if you remember what I said before, I said that for power, we have a formula which says VI. Okay, this is one of the quick formulas that you mostly manipulate. So what is my power? My power is 12 watts. It is given over here, 12 watts. And then what is my voltage? 18.99. And then what about my current? Current, I don't know. I'm looking for it. So I simply divide both sides by 18.99 divided by 18.99 over there. And then what value of current do I get?
0.63.
0.638 over there. So you got your value as simple as that. You got your current over there. Now, the following question said, calculate the reading on the voltmeter. Calculate the reading on the voltmeter when switch S is open. Okay, let's go back and see what they mean. Let me clean my diagram. It's a bit messy, bit dirty. Okay, now I'm sorted over here. Let me go back to the question. The question said, calculate the reading on the voltmeter when switch S is open. Reading on voltmeter when switch S is open. Okay. So now they're saying in this case, we have switch S being open over there. And then now they want the reading on the voltmeter, of the voltmeter that they're referring to is the voltmeter over here. Okay, now this is where you start to think, how can I do this? So sometimes when you're working this, you'll realize that what you are asked or what you answered are
Sir, you are muted again.
okay, it's fine. So yeah, no, it's fine. I'm used to it. That's not a problem. So now what you can simply do is that you are looking for the value of the resistance when the switch is open. Okay, and if you remember, or if you are taking notes, there is a statement whereby I said, I think we were talking about the graphs, when the switch is open, the voltage reads the EMF. When the switch is open, voltage reads EMF. Okay, so what they're simply asking here, they're asking calculate the EMF, because when the switch is open, we find the EMF. Okay, all right, that's fine. How can we find the EMF now? So to find the EMF, we're going to use the formula EMF is equal to I into R plus small letter r over there, like that. So now, oh, okay. Sorry, so now we are going to firstly calculate the total current, because for the total current, IT is made up of A1 plus A2. That's the total current, and it is the current that comes out of my battery over there, and then it splits. The other current goes to A1, the other current goes to A2. So which means I'm going to add 0.75 plus 0.63. What value do I get from the calculator? What is my total current?
1.33.
That's going to be 1.33 over the ampere. So that's my total current.
1.38.
Oh, 1.38. Okay, sorry for that. 1.38. So now that's my total current. What else do I need to satisfy my equation? I need the total resistance now. So in order to find the total resistance, in this case, do we have it? Let me see. I think we have the resistance for the top branch, but we don't have the resistance for the bottom branch. Okay, but we can find it, because for this branch, we have a current of 0.63, and then our voltage, we have a voltage of what? Our voltage is 18.99. So in order to find the resistance, we're going to use the formula R is equal to V over I over there. And then That's going to be 18.99 divided by 0.63. What value do I get from your calculator?
Thirty comma 14.
30.14 over there. That is my resistance. And if you check, it is the resistance for the parallel circuit, not for the total resistance. Okay, so which means now we have the resistance of the bottom branch, which is 30.14, but we also calculated the resistance of the upper branch, or the branch on top, which I think it was 25.33, something like that. I think it was something like that. Yes, 25.33. That's what we got. So now we're still going to simplify that circuit by finding the parallel resistance, which will be our total resistance in this case. What I mean is I'm going to say RP is going to be R for the top branch. Let me just say top multiplied by R bottom for the bottom branch, which is this one, the 30.14 bottom, divided by R top plus OR bottom over there. So it's going to be 30.14 multiplied by 25.33 divided by 30.14 plus 25.33 over there. And then you get a resistance value of how much? What is the resistance value?
13.76.
How much?
13.76.
30 or can you please?
13.76.
Oh, 13.76. All right, thank you. Over there, ohms. So now, in that case, you have everything that you need, because this internal resistance, it was given, it is 1, simply 1. So you're going to simply make your calculation, and then you have your total current as 1.38, and then you have your this internal, your total resistance. Your total resistance is simply 13.76 plus 1 over there. What answer do you get?
$236.88.
200.
Yeah.
No.
No, I got 20.36.
Oh, yeah, I was confused. All right, it's 20.36.
37. 37.
37.
Okay, 37 volts over there. So that's, yes. Okay, I thought that was the question. So that's your EMF over there. So the very important thing that you needed to know in this case is that when the switch is open, you have the EMF. That's what you have over there. So if there is no question regarding that question, we can simply move. We can simply move forward. Now we have this question, of which it was question 5.
Yeah.
They said, yes.
May I ask if the switch is closed, what does the voltage read?
Oh, when the switch is closed, your voltage is going to read the external voltage. your V, okay, let me come back over here. In this case, because the switch is closed on the equation itself, the switch is closed. This V over here, it is going to read the external voltage, because there is a confusion that some of you will say, hey, it is connected across the internal resistance or across the battery. No, that voltage always reads the external voltage. I hope I make sense over there.
Yes, sir, you do. Thank you.
All right.
Sir,
Yes.
Sir,
can I
please
please
repeat
go
what you
first?
just said.
Okay. Let me add something over here. Let me add something. Let's say I have V2 over here, and then this is V1. And then this is V1. So what you will realize is that I said, just that this one is that the circuit itself is a bit complicated. But okay, what you will see is that this is a combination type of circuit. So in a case like this V2 reads voltage or potential difference, let me just say voltage, across 20 ohms. Okay, is the voltage across the 20 ohms. But this one over here, of which I said it is my V1, that V1, it reads the external voltage, yes, external voltage. V2 reads a voltage across the 20 ohms. If I had another resistor over here, of which let's say it was 5 ohms, and then there was a resistor, not a resistor, a potential difference, a voltage connected here, of which maybe let's say it's V3, then it means that V3 was going to read voltage across what? Across the 5 ohms. Across 5 ohms. So the only difference is because this one is connected across the battery, it actually measures the potential difference on the external circuit. V1 is actually going to be the sum of all the voltages in your circuit, because we can't say it measures the voltage of the battery or the internal voltage, because it is not actually connected on inside the battery. It is not inside the battery. I mean, it is not connected something like this. It is connected on the wires. So on the wires, we find the energy that is being distributed on my circuit or on the external circuit. Are you guys fine with what I'm saying?
Yes, sir.
No.
Okay. All right. Let me come this side. Let me come this side. Let's say this is just a simple circuit. I have a resistor, I have my battery over there, something like that. That's V1, that's V2 over there. Then you know that potential difference is actually measured across a resistor at a certain point of your circuit over there, because you can't connect a resistor on the circuit itself, because not a resistor, sorry, I mean you can't connect a voltage on the on the circuit itself. Like, I mean, you can't connect a voltage like this. A voltage can never be like that, because a voltage has a very higher resistance. It does not allow current to flow at all. it will never allow current to flow at all. So we either connect a voltage in a parallel way to the resistance. Okay, so if you see V1 is parallel to my R1 over there, for example, and let's say this is R2. So what happens is the voltage of V1 is measuring the potential difference across R1. Okay, and then V2 it is measuring the potential difference across R2. That's what happens in every circuit. Let me see if I have any other diagram. Yes, V2 in this diagram, it is measuring the potential difference across the resistor X over there. But this one, my V1 over here, this V1, it is actually measuring the voltage that is distributed or that is being delivered to the external circuit. It is actually measuring if I have a voltage over here also, which is V3, for example. So V1 was actually going to be the sum of V3 plus V2. It is actually the external voltage of the circuit, not internal. Because internal voltage, we find it on the battery, but this V1 is not connected on the battery. It is connected on the wires, on my wires over there. So it is on the external circuit. It measures everything that is on the external circuit over there. If I don't make sense in this case, I don't know what else to explain. Or if there is, okay, are you fine with what I said, or you are still confused?
I'm fine.
Okay, all right, it's fine. So now let's go back to our question.
May I please ask a question?
Yes.
Can you please go back to the previous question?
Okay, this question.
No, the one that we did.
All right.
Yeah, I'm sure we got that the top branch, the effective resistance, all of it was 25.33.
Yes.
Now, if they told us that R, there is the one R, the unknown R is also the same as 25.33, was it going to be efficient for us to just divide the current?
Yes,
Because
they were going to share the current equally because they're equal and the voltage is the same. So you are going to, even if you calculate, you are going to get the same answer.
Thank you.
Yes. And yeah, that's it. And for those who are more interested in learning just for your own sake, let me also edit in this case for learning purpose. Here we got our R value as 30.14. And then here for the entire branch, it was actually 25.33. But let's say I want to find the current that is moving through A2. Okay, I know the answer is, where's the answer? We have it somewhere here. And yeah, we have the answer. It was 0.63. I know it. So I want to make sure or verify that we get the same answer using the current divider rule. I'm going to say, I'm looking forward for the current I passing through resistor R. Let me just write it like this. I'm looking for the current passing through resistor R. So the way I do it, I'm going to say it's equal to, I'm going to write the resistance of the current that, the resistance of the current that I don't want, or the resistance of the branch that I don't want. Okay, what I'm saying is I'm looking for the current that is A2. I'm looking for A2, but I'm going to write the numerator as the resistance of the branch that I'm not looking for. What I'm saying is because I'm not looking for the current passing through A2. That is the branch of, that is the resistance of the branch that I'm not looking for. Resistance of the branch that I'm not looking for, or that has the current that I'm not looking for. What I'm saying is, your numerator, you are going to say 25.33. That is for the branch that you're not looking for. Okay, so then your denominator is going to be the addition of all, or of the parallel branch, only the parallel branch in this case. So the parallel branch, it is 30.14 and 25.33. That's going to be 30.14 plus 25.33 over there. When you do the calculator, what are you getting? And also let me write this other side as current passing through A1 as 30.14 over 30.14 plus 25.33. What answer did you get for the first one?
0.46.
Are you sure?
Yes.
Okay, 0. Oh, sorry. I forgot to multiply by the total current. Yeah, yes. I see why I made the mistake. You also multiply by the total current, of which it was, the total current was, what is the total current? Total current. The total current is 0.63 plus 0.75. I think it was 1.33. That was the total current. You also multiply by the total current, 1.33. Are you getting the same answer?
The current was 1.38.
Oh, sorry, 1.38. So you're going to multiply by 1.38 over there. And then what value do you get?
0.63.
Okay, 0.63 over there. Here we had 0.63. Okay, it's fine. And then what about this one? You also multiply by 1.38 over there.
0.74.
0.75 over there.
5.
Yes, 0.75 over there, of which it is that one that we got over there. So in simple, you can, even though they don't allow you to do this formula or to write this formula, you can just use it to verify, because sometimes you will go a long way to find the current there and there, but you can just use it for as long as you're working in a parallel branch. The way you do it, on top you write branch for branch not needed. Okay, you see, here I was looking for the current passing through A1, but the numerator was for the branch that I was not looking for, 30.14. This is the resistance of the branch that I was not looking for. And then you divide by the sum of the two resistance. You just add them. You add the two branches as like 1 plus 1. You just add them. Just addition. And then you multiply by IT, by the total current, IT. This is the total current. So you can just do something like that, just to verify over there. Yes.
Can you please explain the difference between EMF and V internal?
Okay. All right. So the EMF, okay, let me start here. Let me come here. The EMF, this is the maximum energy provided by battery. And then V internal, this is voltage. This is the voltage consumed when this for this one, this is not a formal definition. This is not a formal definition. This is just based on my understanding so that you understand. Okay, you will go and do research on the formal definition. So this is the voltage consumed when current is flowing over there. So, okay, what do you mean, say? You're going to buy a battery, a simple battery. You want to connect maybe a torch, for example. When you buy that battery, outside that battery, it's written 12V as your EMF. That's the EMF of the voltage. It is the maximum energy that the battery can provide before it is no longer working. Before it stops working, it can provide 12V. But scientifically or in real life, what happens is that battery will never ever provide 12 volts of energy. It will never provide that energy of 12 volts. So what rather happens is your battery can only provide something like 11.9 V. When you're using that battery, you find out that after providing 11.9 volts of energy, your battery stops working. Okay, your battery stops working. So this provided energy, V, this is going to be your V external, the one that is provided, 11.9. V external. Why V external? Because it was distributed outside the battery. It was provided outside the battery. It is V external. It was sent outside. External means out. But because it was written 12V and it only used 11.9, what happened to that other voltage? That is the voltage taken by the battery itself. Inside the battery itself, there is a resistance of which we call it the internal resistance. Internal means inside. That is the resistance inside the battery. And you know that a resistance has a certain amount of voltage. That is why in a circuit, in each circuit, we are going to have voltage. We are measuring the voltage on this resistance. Okay, so what I'm saying is the battery itself also have a resistance, which is the internal resistance, and that internal resistance, it takes out something from that EMF, and the internal resistance, we find that it took 0.1, because if I add 0.1 plus 11.9, I will get 12 volts, which means this 0.1 is going to be my what? My V internal, which means that is the voltage inside the battery. So what normally happens sometimes when they ask these questions, they're going to do it in two ways. Sometimes they will either say the voltage, okay, and get you will be having your EMF. Let me use the same explanation. You have 12V as your EMF. Let me say this is the EMF. EMF is equal to 12 volts. And then they say the switch is open. But on the other statement, then they said, when the switch is closed or when switch is closed or something, the voltage decreases by, or the voltage decreased to. Those are the very important words. I don't know why today I had forgotten them. I mostly make sure that I explain them because they almost reigned my entire career or my entire life. So to make sure that you're on the safe side, I'm going to give you the information today. When the EMF is set to decrease by or decrease to, okay? Decreases by, decreases to. Okay, you know that if I say decreases by, I'm going to say decreases by or decreases by maybe 0.1. Okay, and then this one decreases to, that value is going to change to something else. The given value will change to 11.9. So what I'm saying is my EMF is going to be made up of V internal plus V external over there. And then V internal, I said it is 0.1. And then V external, I said it's 11.9. Now, look at this. If they say the EMF decreases by, your EMF has decreased by 0.1. Where is that 0.1? Because I was having an EMF of 12. My EMF was 12. And then that 12 decreased by 0.1. Where is that 0.1? That 0.1 was taken by something else, of which it is your internal resistance. Okay? Which means whenever they say a value decreased or decreases by, that is your internal voltage. But if the value is set to decrease to, or they say your EMF decreases to, your EMF decreases to, your EMF was 12, and then it decreased to 11.9. And then that means that 11.9 is your external voltage. Okay, so make sure that you understand the difference between by and to over there. All right, so let's go back there. If you have a question, you are free to ask. It's not a matter of doing many questions, it's a matter of you understanding what you're doing. All right, now we have our question, which was 5.1. They said in the circuit below, the battery has an EMF of 12 volts and an internal resistance of 0.2. Okay, fine. Then I'm not reading the last statement. I don't want to embarrass myself with my English. Then 5.1.1, define the term EMF of the battery. You know that is the maximum energy provided by the battery per unit charge. Okay, then switch S is open. This one, switch S is open. Switch S is open. A high resistance voltage is connected across A, B. What will be the reading on the voltmeter B? What will the reading on the voltmeter be? Okay, guys, my people, my great people, as long as if the switch is open, we read the EMF. We have our switch open, which means the voltage that is connected, the voltage that will be connected is going to measure what? The EMF. For as long as switch is open, we measure what? The EMF. So our voltage reading is going to be 12 volts. I hope I'm clear. Then now, 5.1.3, switch S is now closed. Switch S is now closed. That switch is now closed. The same voltage is now connected across CD. Okay, they said that the same voltage is now connected across CD. What will the voltage be now? Okay, guys, what happens is, you never heard me saying we connected a voltage somewhere where there's no a device. I mean, Ori, you have never seen a circuit whereby there is a voltage connected without a resistor. Okay, what I'm saying in simple is, we don't connect a voltage in a conductor, or we don't connect, we don't actually, okay, we don't actually measure the potential difference across a switch. That's what I'm saying in simple. I know sometimes I can come up with weird statements, so I decided to make it simple and straightforward. What I'm saying is, we don't connect a voltage. We don't connect a voltage across a switch, because in this statement they said voltage is now connected across point CD. So we don't connect voltage across a switch or anywhere in the wires, something like this. There must be a device. There must be something there. As long as it's not a switch, something else. So it means that the voltage that we read here is actually going to be 0. the voltage that we measure across the circuit is going to be 0 because there is no device that we are actually measuring. There's no device that we measure at all in that case. There's no potential difference in that case. And yeah, that's 0V over there. So anyway, whereby you find them connecting a voltage in a conductor without any device in the middle, except a switch, that's going to be 0 volts. If the switch is closed, if the switch is closed, if the switch is open, that's the EMF. So when switch S is closed, the potential difference across the terminal of the circuit is 11.7. Okay, the potential difference across the terminals of the battery is 11.7 over there. So what they're actually saying in simple here is that 11.7 is your what? 11.7 is actually your V external, because they said across the terminals of the battery. So it is actually connected something like that across the terminals of the battery, V. And I said that V, it measures the external voltage distributed outside. It measures the external what distributed outside the battery. But wanna guys, to make life simple, we had our EMF. EMF was 12. And then we have V external, which is 11.7. And the first question wants us to calculate the current in the battery. Current in the battery. But don't forget that in this case, I know that EMF plus or EMF is equal to V external plus V internal. And then what is my EMF? Yes.
How are we going to see that 11.7 is V internal? Let's say maybe they said something, then we are saying that 11.7 it's V internal. Again, now you are saying that 11.7 is V external because you are saying that they are connected on the terminals of the battery. How are we going to see if it was V internal?
Everything is on the language. Everything depends on the language that they're using. That's why I gave you the words decreases to, decreases by, and then but for this case, the question was in a different way. They said across the terminals of the battery, across the terminals of the battery, of which it means outside the battery. So I don't know in what way they were going to bring the language to show that it is, but for my case, I think they were going to say something like the potential difference or the voltage decreases by maybe 0.3. That's how I was going to assure that it's the internal voltage, because if it decreases by, that means the value that it decreased by, the value of 0.3 is actually the value taken by the internal resistance, which is the internal voltage over there. So to answer your question, just be smart. Make sure you understand the English that they're using when it comes to the voltages over there.
Okay, sir.
All right. So our EMF in this case is 12, and then our V external is 11.7. What we can get is V internal. That's what we can get. So when you take this to the other side, it's going to subtract. So you're going to have V internal being equal to 11, not 11, 12 minus 11.7. And then I think you get 0.3 volts, of which this 0.3 volts is your internal voltage. Listen, it's internal voltage, right? And you also have the internal resistance, right? Okay, it's fine. What did I tell you about the internal resistance? I told you that internal resistance always raises the total current. That is one of the first statement that I said when I was doing the EMF. I said that V internal raises the total current because it has the internal resistance over there. Okay, so what is my internal voltage over there? That's 0.3. And then what is my current? It's I don't know. What is my internal resistance? That's 0.2. So I simply divide by 0.2 so that I can be left with I divided by 0.2. What answer do I get?
1,5.
That's going to be 1.5 A. So this one, that's my total current in the battery. That's my total current over there. Now the second question says, calculate the effective resistance in the parallel branch. They mean this one. So you're simply going to say RP is equal to R for 10 multiplied by R for 50 divided by R10 plus R50. You know this formula. You know this formula very well. That's 10 times 15 divided by 10 plus 50. And what answer do you get? Can I please get the answer, my good people?
6.
6. All right.
Yes.
We got 6 ohms. Don't forget the unit, because the moment you just write 6 and then there's no unit, it's like we're calculating tomatoes. And I don't think in physical science they can ever ask about tomatoes, of which means whatever that you did is wrong. Okay. That's just a joke, but it's also reality. Yeah. Okay. And then the following question is, calculate the resistance of resistor R. The resistance of resistor R, of which what is that resistor? How can I find this one? So in order to find this one, it means that you can simply find the total resistance of the circuit. What do you mean say? We can find the total resistance of the circuit, and then we subtract 6. We subtract the parallel branch, which is 6 ohms over there. So which means in this case, I'm going to have, okay, how will I find the total resistance? Okay, well, you have the total current, which is 1.5. Okay, and then you have your EMF, which is your EMF is 12 V.
Sir,
And then what? Yes.
before you proceed, I have a question.
Okay.
So now, do we consider the voltages or the voltmeters that you have now inserted on our circuit, or do we exclude them right now as we are calculating?
Oh, you can you repeat your question? You are saying that the voltage is,
I mean, the voltmeters that you've added, like that, that one, yes, that one, and the other one over there, and the other
or
one
this?
that you have put it on the, yes, sir, those two.
Okay, this one, it is not necessarily there. I was just showing there. But for this one, even though you don't show it, it's fine. But at some point, this question or this statement, that statement was just there to show you that we have an external voltage in that circuit. And you must know that an external voltage must be connected in this way. It must be connected across the terminals of the battery, even though it is not connected, but you have an internal resistance, you can simply predict that it's there when you're doing your calculation. So what I'm saying is, if you leave your question like that and you make the calculations, when you use V external of 11.7, that value that you are using, it is for a device that was supposed to be connected like this, but unfortunately it's not connected. So what I'm saying, that's how V external must be connected in a circuit where there is internal resistance. So in this case, let me just remove it because it's not there. Yeah, we can leave our circuit like that. We're still good over there. So here I was still saying that we have an internal resistance of 0.2 ohms over there. So in this case, we can simply find the total resistance, okay? Because we know that EMF is equal to I into R plus R over there. And then our EMF is 12. And then our current is 1.5. And then what about total resistance? We don't know. And then, okay, remember this one. This is the total resistance, not this R, not that R. It's the total resistance, the sum of those resistors. Okay, so here my internal resistance is 0.2 over there. So here I just work out the maths. It's 12 is equal to 1.5 R. And then what is 1.5 multiplied by 0.2?
0.3.
That's going to be plus 0.3 over there. And then I take this to the other side. I'm going to have 1.5 R is equal to, when I take this to the other side, it's going to be negative, and then I subtract, which means I'm going to get 11.7 over there. 11.7. So somehow logically, okay, yes, then divide by 1.5 and then divide by 1.5. And then what is your resistance value?
7.8.
7.8 ohms over there. So now, in this case, this is RT, okay? It is RT, the summation of the resistors, resistors in total. So what you do in this case, Angiti, you have simplified this. You have simplified this resistor over here into what? Into 6 ohms over here. You have simplified that one. So now, at the end of the day, those two resistors, 1 and 2, resistor 1 and 2, they're in series with each other. To find resistance in series, total resistance, IT is equal to R, of which it is that one, and plus R6, of which it is that one. So which means, what is my total? My total is 7.8. And then what is my R? R, I don't know. And then what is that one? It's 6. So I'm simply going to take 6 to the other side, and then it's going to be 7.8 minus 6. What is the value? What is the value that I get?
1.8.
1.8 over the ohms. As simple as that. So that's the value that you get. So now, in that case, you have got the value of